evening, everyone. I hope that you guys are doing well. And we are hopefully getting close to finishing our very long chapter here on gas laws. So we are tonight going to talk about root mean square velocity. And it's a really fancy name for just trying to figure out how fast, what is the speed of a gas molecule? How fast are they moving? Velocity is something that you should recognize from physics, or if you're not in physics right now, from ninth grade or even middle school. And remember that velocity is equal to a distance over time. And so in our case, it's going to be a meter over a second. And so we're going to try to take a look at how fast these gas molecules are moving. And how we're measuring that is called our root mean square velocity. And this is signified by the capital letter U for velocity, root mean square. And this formula is on your AP gold sheet, so it's not something that you're going to need to remember or memorize. You're just going to need to understand it. So as we take a look, it is the square root of 3 times RT over a capital M. So what are all of these variables? So R is still going to be our gas law constant, but because we are talking about velocity, we need to talk about energy. And so a unit of energy is going to be our joule. So in this case, our R is equal to 3.145, and this is going to be joules per mole Kelvin. And again, this is also on your gold sheet, so it's not something that you're going to need to remember. You're going to need to know, though, that temperature is still in Kelvin, so that's not changing. And this big M here is for molar mass. But in molar mass, it's going to be, instead of grams per mole, it's going to be in kilograms. And so the reason that it has to be, well, that's a nice K there, the reason that it has to be in kilograms is because if you recall, a joule is equal to a kilogram meters squared per second squared. And so because we are here in our unit of energy, we also need to cancel out those kilograms, so we need to have our mass in the same variable. So what does this all mean? Well, if we take a look at the kinetic molecular theory, we know that all of the molecules are moving independently of each other, the gas molecules. They collide with each other and they collide with the walls of whatever container that they are in. So you can see, again, we talked about that they move in straight line motion, they move independently of each other. And so this is just a picture, a good picture of imagining a gas molecule be the molecule again of you're getting in everyone's way and you're bumping and causing collisions. Another way to look at this is that if you think about cheap perfume versus expensive perfume, cheap perfume has very light molecules. So think about those light molecules being inside of this box. They're going to travel faster because they have less mass. They're going to be bouncing around. That's why you can smell cheap perfume for a long ways away. Where expensive perfume, it's going to adhere to your skin a little bit better. It's going to stay put. Those molecules are much heavier, and so it's not going to be as obnoxious smelling. So this has to do with the movement of the gas molecules. So the average distance a particle travels between collisions in a gas sample is called the mean free path. So all this is how far are they moving. Now, some of the things that you should be thinking about, well, what is this based by? What is it determined by? I guess I'll use the word determined. Well, we know that's going to be determined by our volume. Well, what is the space of the container? Where is that gas traveling? It's going to depend upon the temperature of our situation. We know that gases are greatly affected by temperature, and if that's the case, then they're greatly affected by pressure. And then we also know that this is also going to be a factor of the number of particles. And the next slide here is going to show you that, what I mean by that. So all of these things are taking a look at the average distance a particle travels. So if we have all these factors, volume, temperature, pressure, number of particles, so I hope you're thinking that these gas particles probably aren't traveling very far between a collision, and you're exactly right. So if we plot this out a little bit, you guys can see that we have some oxygen molecules given at STP, so we know we're at 1 atmosphere, 273 Kelvin, and we can see the relative number of oxygen molecules with a given velocity and its molecular velocity here. Now, not every single molecule is going to have the same velocity because of all the factors that we just talked about. Now, what they actually have found, if we take a look at a plot of nitrogen, molecules that have a given velocity at 3 different temperatures. So you can see that something at a pretty low temperature here, 273 Kelvin, as compared to these other 2 temperatures, the velocity that those gas molecules are going to have fall in a much smaller range than if you take a look, if I grab a different color here, then if you take a look at this wide range here of all those gas molecules when you increase the temperature. So these peaks represent the most probable velocity, but again, you can see that as we increase the temperatures, things are behaving less ideally, which is what we have been talking about. So it increases this range of velocities, much harder to pinpoint. So then we're talking about in this section effusion and diffusion. Diffusion is the rate at which gases mix. And then effusion is the passage of a gas through a tiny opening into an evacuated chamber. And so how fast is this going to go into this chamber? And so you could kind of think of it like how quickly does an odor disperse throughout a room? So here's another little picture for you to think about. So the effusion of a gas into an evacuated chamber. So we have these gas molecules, kinetic molecular theory. Remember, they're bouncing off each other, be the gas molecule, there's colliding, there's some pressure in here. Obviously, if we increase the temperature, they're going to be moving around even more rapidly. Well, is that going to affect how quickly it can go through this gas chamber? Absolutely. And so why is it going to go through this and how fast is it going to go through? Well, here's Graham's law of effusion. So he is saying that the rate or the speed, all right, of gas 1 is equal to the ratio of the rate of speed of gas 2. And you can see here that we are talking about the capital M. So the unit is kilograms per mole. But we don't really need to worry about that because you can see that because it's a ratio, they are going to be canceling them out. So if we take a look at and just draw something simple like you guys just saw in the last example here, that if we just draw a very simple little chamber and I have an opening here and I'm going to put 2 gases into my chamber, and one of the gases I'm going to have is CH4, methane gas. That's what we have in our Bunsen burners. And then the other gas that I'm going to have is chlorine gas. Now you can recognize in both of these situations that they have different mass numbers. So they are going to try to travel through my gas chamber. Well, if I take a look at methane, it has a molar mass of 28.0, and the mass of this is going to be 71.0. Now again, I just took these right from the periodic chart. We don't really care, I guess. Technically you should have it in kilograms, but because they cancel out, I'm just going to use the values that we are comfortable with. So then if I take a look, I am looking at molar mass of the second one divided by the molar mass of the first one. I'm going to take the square root of that. And so if I substitute that in, I would have 71.0 divided by 28.0. And this is my ratio of my chlorine gas to my methane is equal to 1.59. All right, so what does that tell you? That tells you that the methane gas is going to effuse 1.59 or 1.6 times faster than the chlorine gas. Now, if you think about it, we're really not going to get into all these technical numbers here, but if you wanted both of these gases to get to a certain point at the same time, you would have to release the chlorine gas first because it's much slower. This is like a semi sitting at a stoplight versus a little sports car at a stoplight. Can they both get to the same point at a point in time? For sure. They're not going to get there at the same time. So if you want the semi to get there and these to get there at the same time, you're going to have to release this gas first because it's going to be a little slower getting there. So let's see, the distance traveled, kind of the same thing. That's just what I'm talking about there. You can talk in terms of the speed or the distance traveled. So here's an example of this. So we have NH3, ammonia, and hydrochloric vaporized acid from cotton plugs diffused towards each other react to form ammonium chloride. So what this means is I would have one gas on this end of the tube, I would have another gas at this end of the tube. They are released and they're going to follow along the chamber, and when they come together they form this reaction and they formed ammonium chloride. So if I'm going to again take a look, let me put a different color here that might be easier for you to see on this dark screen. So if I'm going to put ammonia over here and I'm going to put hydrochloric acid vaporized over here, this would be 35, this would be about 36, almost 37 as its molar mass, and here is 17. Well, this one's going to move much faster. This is like the little sports car. So if I am worried about them hitting this at the exact moment that I want to create this chemical reaction, I'm going to have to release this one first because it's much heavier. Logically, just think logically and you will get this. Okay, that is the end of this first part. We're going to have one more podcast on real gases and then we will be done with this chapter. Have an excellent night.